So this is problem 13.2 out of Taylor's Classical Mechanics textbook. Chapter 13 is a very important chapter, and I don't have any videos, I don't believe, on this section, which covers Hamiltonian mechanics. So I'm going to do that with this problem. It's a very simple problem, but I think it'll show you the way that you go about solving these so that you can apply this to more difficult problems, which hopefully I'll do in the future as well. So in this case, it's one-dimensional, a particle m moving vertically under the influence of gravity. And it wants us to find our Lagrangian, the generalized momentum, the Hamiltonian, and the Hamiltonian's equations of motion. So in general, a good place to start is to find your Lagrangian, since the Lagrangian is part of the definition of the Hamiltonian. So just like in chapter 9, the Lagrangian is your kinetic energy minus your potential energy. So in this case, it's going to be just 1/2 mx dot squared minus, and then our negative, so plus mgx. So that's the potential energy due to gravity. Your momentum, your generalized momentum, is the derivative of your Lagrangian with respect to x dot. So that's pretty simple, just power rule, mx dot. From here, you can define x dot as p over m, dividing both sides over by m. Okay, so that's good. Now our Hamiltonian is p times x dot minus our Lagrangian of 1/2 mx dot squared minus mgx. So now what I'm going to do is I'm going to substitute p over m everywhere I see x dot. So then I'm going to have p squared over m minus 1/2 m times p squared over m squared, and then minus mgx. So your masses drop. P squared over m minus p squared over 2m is just positive p squared over 2m. And then we have our minus mgx. So this is our Hamiltonian, and it's in terms of our momentum and position. Okay, so that's great. Now our Hamiltonian equations of motion are right here for x dot and p dot. So we just take some derivatives. So then to find x dot, it's the derivative with respect to the momentum. So that's just a simple power rule. You'll get p over m, which is what we had here, so that's good. So we took the derivative of the Hamiltonian with respect to p. P dot is minus the derivative of the Hamiltonian with respect to x. So that negative sign will make that just mg. Okay. So now what we could do is we can actually plug this in over here. So p dot, p is equal to m x dot. So then if I take the time, so that's coming from here, just multiplying it. And if I take the time derivative, that'll be m x double dot. So I can plug that into here, right? So I have m x double dot equals mg. The masses then cancel, and I find that x double dot, our acceleration, is equal to g. So that's to be expected, since the problem tells us that it's only under the influence of gravity. And from here, it's a pretty simple, you just solve this equation of motion to get your kinematic equation. Okay? So in general, to solve Hamiltonian problems, you need to find your Lagrangian like we did in chapter 7. Find your generalized momentum. Then you want to plug in for your, I would say usually your velocity. So you plug all that in, get your Hamiltonian, and then you can use Hamilton's equations of motion. And that's all there is to it. So hopefully that helped. And if it did, please like and subscribe. And I'll be posting more soon.